Okay, hello everyone. Welcome to the fifth talk of this semester. Today we have Henry Adams from Colorado State University, and Henry will be talking about Gromov-Hausdorff distances, Borsuk-Ulam theorems, and Vietoris-Rips complexes. Henry, the stage is yours.
Thanks so much. I'd really like to thank Hitesh and Wenwen and the organizers for the opportunity to share. And apologies for the inconvenience a couple months ago when we had to reschedule, but it's great to be able to share virtually. So I'll be speaking about a recent project that I've been involved in relating Gromov-Hausdorff distances, Borsuk-Ulam theorems, and Vietoris-Rips complexes. It's really based off of a recent archive paper by Lim, Mémoli, and Smith relating Borsuk-Ulam theorems and Rips complexes. Relating Borsuk-Ulam theorems and Gromov-Hausdorff distances. We're going to throw in Vietoris-Rips complexes, which is a topic I love. We're doing this in a very interesting sort of like a polymath-style project with folks from Colorado State University, Ohio State University, Carnegie Melon University, and Freie Universität Berlin, or former students at these places. So I'm the faculty at Colorado State, and Facunda Mémoli at Ohio State, and Florian Frick at these two places. And then many of our current and former students and postdocs. So it's been nice to learn from each other. All right, so this is just our advertisement. Certainly people have related Gromov-Hausdorff distances and Vietoris-Rips complexes, so the stability of persistent homology. Just in 2021, this really nice paper came out on the archive by Lim, Mémoli, and Smith using Borsuk-Ulam theorems to bound Gromov-Hausdorff distances between spheres, and I'll survey this paper. I had worked with John Bush and Florian Frick connecting Borsuk-Ulam theorems and Vietoris-Rips complexes. I won't talk so much about this work, but it really gave us the insight we needed together to join all three. So this project is filling in the simplex and relating all three of the topics. They're intricately linked, as I hope to convince you. All right, so let's start with just a definition of Gromov-Hausdorff distances. It's a distance between two metric spaces. So X and Y are metric spaces, but we're going to say what's the distance between them. So think of X as this black curve, for example, and Y is this set of dots. You know, maybe the definition you've seen of Gromov-Hausdorff distance is it's the smallest epsilon, such that if you thicken X by epsilon, you contain Y, and such that if you thicken Y by epsilon, you contain X. Okay, so that's maybe the Hausdorff distance if the spaces are embedded in the same place. If they're not, you sort of infamize over all isometric embeddings of X and Y into a common space. But we're going to use a different definition that's more useful for our purposes, really more useful to the paper by Lim, Mémoli, and Smith that we're working off on. Twice the Gromov-Hausdorff distance between X and Y is the infimum over all pairs of maps, one going from X to Y, one going back, that can be discontinuous. And you want those maps to minimize, right? You want those maps to minimize the maximum of three terms, the distortion of each map and something called the co-distortion between them. So let me first define the distortion of G, okay? So G is mapping from X to Y. Here my X is a two-sphere and my Y is a circle. You look over all pairs of points in X, and then you compare their distance in X to the distance between their images in Y, okay? And then the distortion is, you know, how much have you changed that distance when you map from X to Y? So you find the worst pair of points where the distances have changed as much as exists for this map. And that's the distortion of this map. So that's this term. The distortion of H is going back the other way. we're going to be lower bounding the distortion. And the way we'll lower bound the distortion is just by lower bounding we're going to lower bound the Gromov-Hausdorff distance. And the way we're going to lower bound it is just by lower bounding this term. Okay. So we're not going to deal so much with the co-distortion in this talk. But for the sake of completeness, let me tell you what the co-distortion is. The co-distortion depends on both maps. You look over all points in X and all points in Y. And then you map X, your point little x into your space Y, and you map your point little y back into your space X. And then the co-distortion is how much have you distorted this distance compared to that distance. And the farthest apart those are, that's the co-distortion of G and H. Let me pause here. Questions?
A quick clarification one. Like, are these ideas of like distortion and then co-distortion are these like things from like optimal transport, or because it feels like you're essentially moving your points like to different landmarks, in the other set.
I totally get the analogy, but think of this as like an L infinity version, right? Because you care about the worst. You care about the worst amount that you've distorted the distances. So it's not like a weighted average of how much you've distorted distances.
I see.
It's like you want to find the worst points. How much have you distorted distances for the worst points?
Okay.
So I think you can make something very precise there, but at the very least, the analogy is perfect.
Okay.
But think of like an L infinity optimal transport. I mean, both are sort of defined using correspondences or couplings. You know what I mean? So, yeah.
Okay. Thank you.
Other questions?
Yeah, as a practical matter of computing over all isometric embeddings of G and H, is there actually a easy way to do this, or is it if you had two data sets, actually pretty hard to do?
Very hard to do. It's known to be NP hard to compute Gromov-Hausdorff distances, even between like finite data sets and things like this. So that makes you think, oh no, I don't want to touch the Gromov-Hausdorff distance. It's used all the time in mathematical theory, like geometric topology, but it's also used all the time in applications. So computer scientists want to like register spaces, and align my tooth with another tooth. And they don't use the Gromov-Hausdorff distance exactly, but they often use notions of distance that are inspired by the Gromov-Hausdorff distance. So I would say in applications, it's very important, even though it's hard to compute, because you often restrict things. You look at a smaller class of transformations to align your spaces where you can compute things algorithmically. But you want to prove things about your variant of the Gromov-Hausdorff distance, and that relates to the theoretical properties of the Gromov-Hausdorff distance.
Okay, thank you.
Yeah, so it's an inspiration for a lot of practical work in shape matching. Today, we're going to look at some theoretical questions. We're going to look at Gromov-Hausdorff distances between n spheres and n spheres of different dimensions. So we'll always equip the n sphere with the geodesic metric. So the distance between 2 points is the length of the curve along the sphere. And the diameter of a sphere is pi. So the length of the curve between the North Pole and the South Pole is pi. So this was studied in a fantastic recent paper by Borsuk-Ulam, Mémoli, and Zane Smith that just came out recently on arXiv. Here's our distance matrix of Gromov-Hausdorff distances between spheres of different dimensions. The distance between, say, the 3-sphere and itself is 0. So that's why you have 0 entries along the diagonal. It's a distance matrix, so it's symmetric. And it's known that all of the entries lie between pi over 2 and pi. So you should think of pi as a large distance and pi over 2 as a small distance. And Lim, Mémoli, and Smith prove that, in any row as you go out, the distances converge to pi, for example. Okay. They prove 3 values of the Gromov-Hausdorff distance exactly. And this is really technical work that's really important and allowed us to conjecture a lot of things. And then they give non-trivial lower bounds on the rest of the table. Okay, so let me tell you where 2 pi over 3 is coming from and what these numbers R2, R3, R4 are. So on the circle, let's inscribe an equilateral triangle. What's its diameter? Well, the distance between these 2 points is 2 pi over 3. Okay, 1/3 of the way around the circle. So that's sort of where this 2 pi over 3 is coming from. Okay, and another name for 2 pi over 3 is just R1. Because what's R2? To define R2, I take the 2 sphere and I inscribe an equal, a regular tetrahedron. And then the diameter of that tetrahedron, or the distance between 2 vertices of that tetrahedron, that's the definition of R2. And then similarly for R3 and R4 and R5. So along this super diagonal, these 2 entries are proven to be R1 and R2. These entries are at least Rn. And as you move out in a row, these entries are all at least Rn as well. Okay. They have another bound related to coverings that I'll say a little bit more about later. So eventually, as you move out in a row, this covering lower bound gets better than this constant Rn bound. Okay. Their proof of the lower bounds is using really novel ideas. They're leveraging a discontinuous version of the Borsuk-Ulam theorem. Discontinuous because these maps of G and H in the definition of the Gromov-Hausdorff distance, they didn't have to be continuous. I'll be saying more about their work, but questions so far?
So do they actually find explicit values of R2, R3, R4, and so on?
Oh yeah, a formula is known for this in terms of like R cosine of n over n plus 1 or something like that. Yeah.
Okay, all right.
Yeah. Explicit formulas for all these numbers are known. Let me actually describe this briefly. Okay, so we need a map from the circle to the 2 sphere and a map from the 2 sphere back. The map from the circle into this 2 sphere is just include the circle as the equator. It's not always obvious that that's the best map to use though. The map from the 2 sphere going back, here's the 2 sphere. And I'm just giving you the rough idea of this map. They divide the northern hemisphere into 3 slices. And then they map those 3 slices to sort of these 3 points on the equator. Okay. So each slice maps to one of those 3 points. And then in the South Pole, they do the same thing, except their slices are offset, by a little rotation. And then, each slice maps to one of these. They have other maps in mind that they think should realize the same Gromov-Hausdorff distance, but this is the map for which you can sort of, so far, get the shortest proof. Okay. So in joint work with Sun-Yuk and Facundo and at least a dozen others, we have proven a sort of a slightly generalized lower bound. And I'm going to explain it intuitively now, and then define things more precisely on the following slides. Twice the Gromov-Hausdorff distance between the n sphere and the k sphere is the smallest scale parameter r, it's at least as large as the smallest scale parameter r, such that when you thicken the lower dimensional n sphere by r using a Vietoris-Rips complex, this lower dimensional sphere now admits a continuous odd map from the higher dimensional k sphere. Okay. So a lower dimensional n sphere does not emit a continuous odd map from the higher dimensional k sphere. I'll describe that more. That's the Borsuk-Ulam theorem. But once you thicken it enough, once you've made it fatter and fatter, suddenly it does emit a continuous odd map from the k sphere. So these are our numbers, C and K, we call them. C and K is how much do you have to thicken the n sphere using the Rips complex until you would admit a continuous odd map from the k sphere. Okay. So some, but definitely not all values of C and K are known. Okay. These values that Hitesh asked about are known. Some, but not all values of C and K are known, even though it's a general lower bound relating things to Rips complexes. These values of C and K are known, so we get these new lower bounds. Furthermore, all of these numbers here are also known to be equal to C and K. So our results, I mean, they certainly did it first, but our results recover these lower bounds, not the equalities here, but the lower bounds, and provide some new lower bounds. And as I'll briefly explain, we improve upon this bound in prior work. Florian Frick and John Bush and I had been studying this question, and we proved that these numbers are lower bounded by coverings in projective space. Okay. Coverings in projective space actually give better lower bounds than coverings in spheres. So the kth covering number of a metric space is the smallest radius r, such that you can cover your metric space with k balls of radius r over 2. And you can cover the projective space with smaller balls than you need to cover the n sphere. Right? Because the projective space is like half as much volume. So with the projective space, you can get away with smaller bounds, which means that this lower bound is going to be, in general, larger than the prior lower bound. So it's sort of nice. We get a uniform number, C and K, that recovers this lower bound and improves upon this one. Not too many values of C and K are known. I mean, it's mostly what I've listed here. However, you could conjecture that this is an equality. We certainly do not have complete evidence for that, but potentially this could be a tight lower bound. Potentially this could be an equality. We don't know of any cases where we're strictly greater than. So that was a lot. I haven't even defined this yet or really defined C and K yet, but it's giving you the flavor of where we're going. I'm not going to talk much more about coverings or packings, but questions here? Okay, let's slow down and define Rips complexes and odd maps. Okay, so odd maps first. A Z2 space is just a space equipped with an antipodal map or a free involution. You can map X to its negative. So, prototypical example is the n sphere. You can map a point to its antipode. And then an odd map is just a map between two Z2 spaces that respects that antipodal action, it's an equivariant map. So in other words, in capital X, if I reflect a point little x to its antipode and then map it into y, I get the same thing as if I first map this point into y and then take the antipode in y. Okay. So here's x, here's y, here's x and y. I can map over. And if I, sort of take the antipode in x and then apply f, that's the same thing as first mapping forward into y and then taking the antipode in y. In other words, this diagram creates. There's many versions of the Borsuk-Ulam theorem. The most common one is that any map of the n-sphere into n-dimensional space identifies two antipodal points. But an equivalent version of the Borsuk-Ulam theorem is that there's no continuous odd map from an n+1 dimensional sphere to an n-dimensional sphere. So if I try to map the two-sphere to the circle that sends antipodal points x and negative x to, antipodal points. So f of negative x should be equal to negative f of x. It has to be discontinuous. I have to sort of tear apart the two-sphere if I try to produce an odd map from the two-sphere to the circle like this. Questions? This is sort of Borsuk-Ulam theorem 101. Some of the first things that you'll do in equivariant topology. Let me tell you about Vietoris-Rips complexes. So this is something I enjoy studying. This is what I mean by thickening a space or sphere. X is a metric space. We pick a scale R. We're going to define the Vietoris-Rips simplicial complex, VR of X at scale R. Its vertex set is every point in the metric space. So here my metric space might have 9 points. And so that every point in my metric space is a vertex. And then it has all simplices of diameter at most R, meaning the length of each edge of a simplex has to be at most R. So, these two vertices are close enough, so I add in the edge. And since all three of these edges are here, I fill in the triangle. And since all four choose 2 of these edges are present, I add in the tetrahedron. So I've thickened my metric space, made it bigger. If I increase R, it keeps getting bigger and bigger, as we do in persistent homology. We'll do something a little crazy. We'll build Vietoris-Rips complexes on top of spheres. So now every single point in our sphere is a vertex. Okay. And whenever you have a finite number of points that are within distance R, right? So if this is at distance at most R, then I have a simplex on all of these points. So it's a very high dimensional simplicial complex, but we can still say things about its topology, actually. What's the cartoon version of why Vietoris-Rips complexes are related to Gromov-Hausdorff distances? Okay. We want to prove that this Gromov-Hausdorff distance is sufficiently large. So we want to say something about the distortion of discontinuous maps between spaces. It's really hard for topologists to say anything about discontinuous maps. Okay. Vietoris-Rips complexes allow us to turn discontinuous maps into continuous maps. Okay. So pretend I have a possibly discontinuous map F between two metric spaces. And pretend its distortion is distortion of F. Okay. This allows me to construct a continuous map, a simplicial map, between the Vietoris-Rips complexes. Okay. So pick my favorite scale R, And then I can map from the Rips complex on X to the Rips complex on Y. You know, on vertices, just map a point little x to f of little x. And then on simplices, well, I know how to map every vertex, so I know how to map that simplex. But what I need to worry about is that I need to increase the scale here, okay? Because whenever I have 2 points within distance r in x, they're connected by an edge. So in y, my scale parameter better be at least as large so that they're still connected by an edge in y. Because I can't map an edge in x to 2 empty vertices without an edge in between. How much do I need to increase the scale by the distortion of the map? Right? Because this distance can grow from r to at most r plus the distortion. So as long as I increase the scale by the distortion of this map, I sort of get a nice map on Rips complexes. It's a simplicial map, so it's continuous. Right? So this is like, I mean, this isn't how we came up with this, but this is how you boil it down after the fact. The reason why Rips complexes are good for studying Gromov-Hausdorff distances is you can find topological obstructions about discontinuous maps by taking your discontinuous map and cooking up a continuous map between Rips complexes. And now if I know the topology of these Rips complexes, I can do topology because I have continuous maps between them. Questions here? All right, I'm sort of whizzing through, I realize, but there's some material to cover, but we're getting near the end. The material before we get to the proofs. I've given lots of talks on Rips complexes of circles and spheres, and you know, it is sort of like a 30-minute talk. So let me just give you the flavor for it. We do understand well, really everything about the topology of Rips complexes of circles, and we understand some things about the topology of Rips complex of spheres. Okay, and this is like knowing the topology of these two sides so that I can produce topological obstructions. So in the case of the circle, I'll just describe this briefly. We have our circle and we thicken it. Let's start that again. We have our circle and we're building this Rips complex. Okay, so you thicken it just by a little bit. You get all these edges, you get all these triangles, you get all these tetrahedra, et cetera, but it's just one solid infinite dimensional annulus. Okay, so I thicken a little bit and I still maintain a circle. I thicken more, I still maintain the homotopy type of the circle. Okay. Until I reach this critical scale 2 pi over 3. And the change that happens there is an equilateral triangle fills in. Okay. And this equilateral triangle that fills in, it's sort of like gluing a disc onto my circle, right? That triangle is solid, it's filled in, okay? But I don't glue on this one triangle, I glue on a circle's worth of triangles, okay? So from a high level, I have this infinite dimensional solid purple annulus, but think of that as a solid torus just sitting in 3D. Okay. And to the solid torus, I glue on not only one green triangle, one green disc, but I also glue on another disc in red. Okay. I'll just, draw many more discs in red, and another triangle and another triangle. So I get the genus 1 Heegard decomposition of the 3-sphere. To the solid annulus in purple that's infinite dimensional, I glue on a circle's worth of triangles or a circle's worth of discs. So I've decomposed the 3-sphere as 2 solid tori glued together along their hollow boundary. In any case, when you thicken when you thicken the circle using the Rips complex, after you reach this critical scale, you obtain the 3-sphere. And then after you reach scale 4 pi over 5, you obtain the 5-sphere, et cetera, you obtain the 7-sphere, the 9-sphere, for smaller and smaller windows of scale parameter until you reach the diameter of the circle and it's contractible. So this allows us to figure out some of these CNK values. So here I'm looking at C1, 2K, or C1, 2K plus 1. This is saying, how much do I need to thicken the circle until I attain an odd map, say from the 3-sphere? The circle doesn't emit an odd map from the 3-sphere. That's Borsuk-Ulam. But once I thicken the circle enough, I get the topology of the 3-sphere. And now I do emit an odd map from the 3-sphere. Okay. So the reason why C13 is equal to 2 pi over 3 is that once I thicken the circle by 2 pi over 3 using the Rips complex, I get the homotopy type of the 3-sphere, which now finally does emit an odd map from the 3-sphere. And that's sort of what's going on here. You know, the n-sphere does not emit an odd map from the n+1 sphere. But once I thicken it enough using the Rips complex, the homotopy type of the Rips complex changes when I glue in these equilateral simplices. And it sort of bumps up by 2. So now, you know, this space does emit an odd map from the n+1 sphere and the n+2 sphere. You know, so how much do I need to thicken the n-sphere to obtain an odd map from the n+1 sphere or the n+2 sphere? Exactly that amount. So that's sort of the quick explanation for why our C and K values recover these known values and provide these new values in blue for the lower bound. And that's how we came up with this. I mean, we saw these numbers appearing in the table and we said, this has to do something with Rips complexes. It took us a while to figure out how to try to prove it, but finally we succeeded. Questions here?
So are there any preprints out on the sphere part of, like on Vietoris-Rips complexes of the spheres?
Oh yeah. So I would say there's 2 main references for this. One is, I'll just give you the authors and email me and I can say more.
Sure.
So one is Adams. I'm the second author, Adamaszek. And Frick, 2018. And another is not Lim Mémoli Smith, but Lim Mémoli Okutan. I think this is from January 2020, first appearance, okay. In quite different contexts. So in our paper, we actually work with the metric thickening. And with the metric thickening, we can get this homotopy type. It turns out the value of C and K is unchanged whether you use the Rips simplicial complex or the Rips metric thickening. Some parts of the story are crucial to use the simplicial complex, but the values of C and K are unchanged. Lim, Mémoli, and Okutan are, to my understanding, I mean, Hausmann's theorem says that when you thicken for a while, you maintain the n-sphere. They prove this optimal bound. You can thicken up to here and still get this n-sphere. By connecting this to work of Katz, they can get this new homotopy type for the case n equals 2, but not in general. But they do in general show that the n-sphere, you can thicken up to this amount and it doesn't change the homotopy type. And that's all you need for the application, the lower bound to Gromov-Hausdorff distances. But you do need this homotopy type if you want to know these C and K values exactly.
Okay, so both the papers deal with like n spheres, like in general.
Yeah.
Okay.
And so, yeah, we get this dual homotopy type for the n spheres in general. We can't show that this homotopy type goes further by epsilon, but that's something that hopefully we'll understand soon. They work for n spheres in general, and they show that the n sphere doesn't change homotopy type up to here. And then for the two sphere, they get this homotopy type connecting to work of cats. This is a beautiful paper. They connect Vietoris-Rips complexes to the filling radius by Gromov. And it's a quite deep, complicated connection that's worth understanding for many, many different reasons.
Okay. I guess I have one more question.
Yeah.
Have you like tried to do like Rips complexes for a torus yet? I mean, like using like the product thing and maximum metric, we can obviously get the persistent homology for a torus. But like if we were to just use like, you know, take like a standard 2 torus in C2 and then use like some notion of like a geodesic distance, like similar to how you did it for the circle.
Like the flat metric on the torus.
Sure. Yeah. That works too. Like, has there been any work on it, or?
Yes. So as Hitesh says, if you use that L infinity metric, you know, things sort of work out very nicely. The Rips complex of an L infinity product is homotopy equivalent to the product of the Rips complexes. And Hitesh and Jose Pereira and myself, we all have different papers related to this.
Yeah.
The L2 torus, so, you know, take the flat torus with the standard metric. Michael Adamaszek and I thought about this for a while and tried to do stuff, but no, I mean, really nothing has appeared on this, I would say, and it's a good place to work. I think it's an important question. I mean, even the L1 metric is interesting. So balls look like this. And you can start with like a finite grid on the torus, right? Take a 100 by 100 grid and start there. Yeah.
Okay, interesting. Thank you.
I have some computational evidence for like 100 by 100 grid, you know, with the L1 metric, I think. So I've done some computations there, but nothing proven.
Okay, all right. Okay, thank you.
All right, so I think I have about 11 minutes left. I want to, okay, good. I want to give you, in 11 minutes, a sketch of our proof. So we're trying to prove that twice the Gromov-Hausdorff distance is at least these C and Ks. Namely, now that everything has been defined, how much do you need to thicken the n sphere until you admit a continuous odd map from the K sphere? That's what C and K is. Okay, so this will be our final proof following the sketch by Mémoli and Smith. But really the new thing we added is the generalization of this result by Dubridge and Schwartz and Mémoli and Smith. So in a paper from 1981, Dubridge and Schwartz asked the following question. I know there's no continuous odd maps from the n+1 sphere to the n sphere. That's Borsuk-Ulam. If I do have an odd map from the n+1 sphere to the n sphere, how discontinuous must it be? Okay. They prove a version of this. Mémoli and Smith use their version to prove that if I have a discontinuous odd map from the n+1 sphere to the n sphere, then it must have distortion at least Rn. Okay. So that's how you can sort of see where their Rn lower bound is coming from, right? The Gromov-Hausdorff distance is like, you know, the infimum over all maps of these distortions and co-distortions. But one of the distortions has to, you know, sort of be at least Rn if it was an odd map, but I'll mention how they get around that. We generalize this for maps from higher dimension to lower dimension, where it's a higher dimension of arbitrary dimension, right? Not just n+1 down to n, but we generalize this for maps from K spheres down to n spheres. And you want to get a bound now that depends on K. Okay. And the distortion is at least C and K, this value we've seen. And that's why the C and K bounds, is the lower bound at all these entries in the Gromov-Hausdorff table. So here's our proof. Take a map, an odd map, discontinuous from the K sphere to the lower dimensional N sphere. We're gonna pick a dense finite sample, okay? So it's gonna be epsilon over 2 dense. So every point in the K sphere is, within epsilon of some point in my sample. And I pick my sample to be antipodal so that I can produce a continuous antipodal or odd map. So because this sample is dense enough, whoops, I need bigger balls. Because the sample is dense enough, when I cover my sample by these balls, it covers the entire k-dimensional sphere. So first, I want to map my k-dimensional sphere into this Rips complex on the sample at a very small scale by using partition of unity ideas, right? So this point on the sphere, would sort of map somewhere into the interior of this 2 simplex in the Rips complex. Okay. So there's many such ways to do this and just do this in an antipodal or odd way. Now from the Rips complex on X, I have a map into the Rips complex on the N sphere, right? Because I know how to take any point in the K sphere and map to the N sphere. I just apply F. So any point in the K sphere, just map to the N sphere. For this map on simplicial complexes to be well defined, though, I need to increase the scale by the distortion of the map, as I explained earlier. So what I've now produced is a continuous odd map from the K sphere into this thickening of the Rips complex. Okay. C and K was defined as the smallest scale such that the Rips complex of the N sphere admitted a continuous odd map from the K sphere. Okay. But I've just built such a map. So that means that the distortion plus epsilon must be at least as large as C and K. And that's true for all epsilon. So the distortion of this map has to be at least C and K. C and K was defined as the smallest scale, such that when I thicken the N sphere, I get an odd map from the K sphere. Right? But here I built an odd map, where I've thickened by the distortion. So this distortion must be at least as large. Questions on that? It's a fair bit there. It's worth thinking through. I'm happy to explain more. But let me get to the punchline. So now we can prove our theorem. The Gromov-Hausdorff distance between an N sphere and a K sphere, or twice it, where N is less than K, is at least as large as a small scale, such that we need to thicken the N sphere by that scale to admit an odd map from the K sphere. And here's our proof. It's following the outline that they used, except now we have a generalized Dubin and Schwartz. So this is our definition for this talk of the Gromov-Hausdorff distance. Twice the Gromov-Hausdorff distance is the maximum over all these terms. And you want to look at the best maps you can. Well, this maximum is at least as large as the distortion. Okay, so it's at least as large as the distortion of G, going from the high dimensional sphere to the low dimensional sphere. And we're just going to consider any G. Okay, so it's at least as large as the distortion of some G, the best G you can find, going from the K sphere to the N sphere. In a critical lemma, Lim, Mémoli, and Smith prove that given any map from between spheres, if it has a certain distortion, you can produce an odd map with no larger distortion. Okay, so I have some nice map from the K sphere to the N sphere that has small distortion. I can find an odd map that doesn't have any larger distortion. The way I do it, in fact, is I just take the arbitrary map, restrict it to one hemisphere and then reflect, to make it odd. And amazingly, you don't increase the distortion. It's actually a very short proof. You just sort of write down some distances and you have some pi's minus distances and the pi's cancel, essentially. So it turns out that any map with a certain distortion, I can find an odd map that has the same distortion, no larger. So really, twice the Gromov-Hausdorff distance is at least as large as the distortion of an odd map from the k-sphere to the n-sphere. And now we can sort of use our generalized Borsuk-Ulam theorem. An odd map from the k-sphere to the n-sphere is certainly discontinuous, and it has to have at least this much distortion. That was the lemma before. Okay, let me finish with some comments and then time for questions. So we were looking at lower bounds in this talk. Constructing upper bounds is a whole different game. You need to find maps G and H. And it's really impressive that they found maps giving tight upper bounds for the circle and the two-sphere, the three-sphere. They being Lim, Mémoli, and Smith. One question is, can you find bounds on Gromov-Hausdorff distances between other spaces, maybe G equivariate spaces, using these ideas? There are notions of P Gromov-Wasserstein distances. There are relaxed versions of Vietoris-Rips complexes as well. And Dubridge and Schwartz is a relaxation of Borsuk-Ulam to the discontinuous case. Take other theorems in equivariance topology, like Freiberg. Can you find relaxations of those to the discontinuous case? I'll end there. Thanks so much for your time and attention.
Let's thank Henry for his wonderful talk. If you have questions, feel free to unmute yourself.
I have one question.
Hey, Bears.
Hi, Henry. Great talk. Thank you very much. Okay, can you talk more about the first question, tight upper bounds for these speculations, ideas?
Oh, you mean speculations on what maps might be? Realize it?
So yeah, I mean, so what are the conjectures for upper bounds? It's the same thing, or?
Yeah, okay. So as I mentioned, Lim, Mémoli, and Smith, they produce tight upper bounds here via maps. And I explained this map, and these maps are worth reading about in their paper. It's complicated, but really impressive that they get it to work. They've done a lot of computational experiments, and they found more maps that sort of realize the Gromov-Hausdorff distance, but it's harder to prove things about the distortions of these other maps. So what can I say? All right. So, I mean, this is sort of work in progress by many people. One name I'll mention is Amzai Jeffs. And this is preliminary, but he seems to be on the way towards getting tight upper bounds for half of these. Okay, and I forget if it's that half or the other half. Okay, I think it's this half. Okay, so he seems to be on the way to getting tight upper bounds for these maps. And I mean, I'll just say, roughly speaking, he sort of takes evenly spaced points on the circle or evenly spaced intervals on the circle and maps them to vertices of regular simplices. I think something like that. Okay, so because Amzai is sort of on the way to proving that these are tight, and we also have this value here, right, where it doesn't increase, I think you have to conjecture that these are also tight, right? So these are also conjectured to be tight but unknown. A different map that one might try to build here is as follows. So I think Amzai is working on this on the red entries. A different idea is to work on these purple entries. Okay, so Fakuna Mémoli and Zane Smith have thought about this idea here, and many of us are thinking about these ideas on the other ones. But you have a map from the circle to the odd sphere by theta maps to 1 over, I think, square root of k, cosine theta, sine theta, cosine 3 theta, sine 3 theta, cosine 5 theta, sine 5 theta, cosine 7 theta, sine 7 theta, etc. Okay, so that's a map from the circle into the odd sphere. And then a map backwards could just be, you know, map each point in the odd sphere to its closest point on the curve. It's discontinuous, but that's okay. So conjecturally, these sort of maps might be tight, and folks are thinking about, you know, is there any hope to try to prove this? I mean, maps like this have come up in various people's work. I would say there's a similar story here on these entries, although progress is maybe going slower. All right, so you want to find maps showing that these upper bounds are tight, right? Sorry, you want to find maps showing that these lower bounds are tight. Okay, what are these lower bounds converging to? They're converging to pi over 4. Because as I increase the dimension of the sphere in the simplex, you know, the simplex, these vertices are getting closer and closer to equator. Okay, so these values are converging to pi over 4 as I go down the row. I think the best known upper bounds by Lim, Mémoli, and Smith are unfortunately converging to pi over 2. Okay, and in work in progress, I think Amzai Jeffs has upper bounds that are at least converging to something smaller than pi over 2, maybe 2 pi over 3. But we seem further away from constructing tight maps here. I'm a quote unquote optimist, and I love Vietoris-Rips complexes. So for the purposes of this talk, maybe not for a paper, you know, I'll conjecture that this is an equality always. We don't have much evidence for that, except that we don't know of any cases that are strict, right? But yeah. I mean, it's sort of beautiful, right? These Gromov-Hausdorff questions that these folks, they've really been working for this on a long time. I think it's really important work and really fascinating. And it's cool that they're relating to Rips complexes. So now when you understand something about Rips complexes of spheres, maybe you can say something about Gromov-Hausdorff distances. Vice versa, I think it would be fantastic. And I've told Amzai Jeffs this. It's not inconceivable that he or you or somebody might find maps realizing, you know, a really nice Gromov-Hausdorff distance, right? Maybe using packings or coverings of spheres, and then aha, that might imply something about Rips complexes, right? So it'd be really cool to see things going in the opposite direction. So, I mean, we don't know these values, right? But at least we've connected two formally disconnected sides of the story together.
Okay, thank you very much.
Any more questions for Henry? Okay. In that case, let's thank Henry again.
Thanks so much.